接下来的场次，我们非常荣幸邀请到两位演讲嘉宾，来自 SambaNova 的 Anton McDonald 先生以及 Kwasi Ankoma 先生。他们将为我们带来题为 "When one chip is no longer enough for AI" 的精彩分享。For our next session, it is our great honor to welcome our speakers, two distinguished speakers from SambaNova, Mr. Anton McDonald, Vice President of Product, and Mr. Kwasi Ankoma, Director of AI Solutions Engineering. They will share their insights in a session titled, When One Chip is No Longer Enough for AI. Ladies and gentlemen, please welcome Mr. Anton McDonald and Mr. Kwasi Ankoma.
Hello. My name is Anton.
My name is Kwasi Ankoma, and we're looking forward to talking to you about disaggregated inference.
Yes. We work for a company called SambaNova. In the Intel keynote session with our chairman and the CEO of Intel, Lip-Bu Tan, Rodrigo Liang, the SambaNova CEO, along with Robert Smith, the CEO of Vista Capital, announced Venture Core Compute, which is a new cloud that exists for the purposes of catering for Vista's portfolio companies, as well as other companies that embrace this idea of heterogeneous disaggregated inference. What we do at SambaNova is we make chips, systems, and software that enable the next phase of inference and particular parts of the next phase of inference that we're going to dive into. So there has emerged this new category of inference called premium inference, and this isn't just us that are saying this. Jensen Huang at GTC 2026 in March talked about this idea of premium inference, where we have large models. Models are getting larger. All of the frontier models, which are closed source today, are trillions of parameters. And now the best open source models are becoming bigger than 1 trillion parameters. DeepSeek V4, as an example, Kimi K2, and new models that'll come from other open source providers. All of those at the frontier will be of that scale, and that is because bigger models are better models. But there is another vector of intelligence beyond just the size of the model, which is how many tokens can I generate? The more models think, and thinking is just generating more tokens in sequence. The more these models think, the better the quality of the outcome, the more intelligent they are. So the combination of these two factors mean that you can get big models, but if you run them slow, they will not be at the true frontier. Or you can run small models and you can run them fast, but again, these models aren't capable enough, even if they're able to think more, to really push forward what the frontier is. And so our contention is that the combination of these two things, big models running really fast, is the definition of premium inference. And the battleground that exists now is who can offer that best. And as a service provider, of which there are many, Vector Core Compute is one example. And this was catalyzed by someone in the front row here, Landon Downs, from Cambium Capital, who's a board member of ours, and has defined so much of the strategy around what this new idea of Vector Core Compute really is. But they're trailblazers, and more will follow. Because as a service provider, if you just focus on commodity inference, if you just buy GPUs, you're not differentiated. You're going to be in a race to the bottom, because what you have and what your competitor has is the same thing. And these are the natural conditions of commodity markets. So you focus on premium inference, but if you try to do that on the stacks that exist today, running purely on GPUs, your cost will be very, very high. So yes, you charge more money, you have more revenue, but your cost explodes because as you increase speed, as you run bigger models, you generate fewer tokens per system. This is just the natural Pareto paradox that we all are becoming more and more aware of. With premium inference running the decoding part of inference on RDUs, you're able to get premium inference revenue, but without this huge cost. So ultimately, you have the ability to expand your margins and differentiate from your competition. The other challenge that we are seeing today, which is a result of the emergence of this category of premium inference, is that frontier AI labs are compute starved. And it's not just the frontier AI labs, but these are the extreme examples. Anthropic has achieved historic revenue growth over the last number of years, from 1 billion in ARR in 2025 to 47 billion in ARR in May of this year. The only thing stopping them from growing even faster is they don't have enough compute. They launched fast mode of Claude Opus, their frontier model, earlier this year. 6 times the price of the normal Opus, same model, just running twice as fast. And they charged 6 times more for that. And immediately there was so much demand. But the problem is servicing that demand. And by the way, that is the most profitable SKU that they have. So they want to service as much demand on fast mode as Opus as possible. But they are constrained on compute because running fast mode on GPUs is expensive. That's why they need to charge 6 times more, because it's so expensive to run. Similarly, OpenAI are experiencing insane growth. They have over 800 million weekly active users today. And they are also embracing the idea of low latency inference, as seen with in their deal with Cerebras. So the culmination of all of these things, the fact that premium inference is what matters, but premium inference is less computationally efficient than slow inference. Running smaller models or running those models slower means that we are entirely inhibited today by the amount of compute that's available. So we believe that we have the answer to this problem. RDUs are R-chip reconfigurable data flow units. And we believe, and this is a blueprint that has been embraced by Vector Core Compute, is that you should take decoding away from the GPU. GPUs are incredible computing machines. They are the best system for training, and they're the best system for the pre-fill stage of inference, which is processing the input tokens, because it's a compute-bound problem that's highly parallelizable. The decoding phase of inference is a memory-bound problem. And so we are going to demonstrate today, why running decoding in RDUs is a better approach, which are going to free up your GPUs, expand your capacity to allow for more inference and more premium inference. The reason we can do this is because the Pareto paradox that I mentioned earlier, where you have speed on one axis, throughput on the other axis, are naturally at odds with each other. If you run inference on GPUs today, decoding on GPUs, you can get really good throughput. You can serve lots of concurrent users. But each user will experience very slow interactivity. They will generate tokens slowly. Alternatively, you can use SRAM-only chips, such as those from Groq, who are now part of NVIDIA, or from Cerebras, that can allow you to generate tokens really, really fast, but with very small throughput because they don't have enough memory. Conventional wisdom is that to get that speed, you need to put things on the SRAM. We are dispelling that myth at SambaNova, and that allows us to optimize on both the speed and throughput vectors, such that we can offer premium inference on decoding at really big scale. So our contention is NVIDIA and Grok, this approach that was proposed at GTC this year, is inhibited by the fact that the LPU has very, very small memory, so that they need to split up decoding into the attention phase and the FFN phase, which is going to make it very challenging to operate at the frontier. Cerebras, similarly, is really good at running small models. They really struggle on big models because, again, small memory inhibits your ability to scale, to have bigger models running at higher throughput. Only SambaNova RDUs can solve this problem. And to demonstrate how we do this, we are going to play a video.
Using AI agents to turn insights into actions is redefining software. Agents plan, reason, call tools, and execute. Every action demands faster inference. GPUs are designed for compute-heavy workloads like training AI models. Inference, though, depends on efficient data movement. On GPUs, inference runs one kernel at a time, with intermediate data sent back to memory before the next operation begins. That adds delay, burns power, and at scale, turns latency into the bottleneck. So we built something different, the RDU, or Reconfigurable Data Flow Unit, designed specifically for large-scale AI inference. 3-tier memory keeps large model pools in DDR, moves active weights through HBM, and keeps activations close to compute in local SRAM. A single RDU processes inference through its spatial pipeline, with execution streaming continuously across the processor. When 16 RDUs are connected, that execution extends across the system. Together, they operate as one unified inference engine, built to run large models efficiently at scale. Parallelism happens at multiple levels across the system. Pipeline parallelism keeps different stages of execution moving in sequence. Tensor parallelism splits a single operation across chips at the same time. Expert parallelism distributes sparse model workloads efficiently across the architecture. At full scale, 256 RDUs work together across racks, generating thousands of tokens in parallel. With more chips, the system is more likely to operate in the Goldilocks zone, where throughput and generation speed per user stay in balance. Unlike GPUs, which run inference kernel by kernel with communication overhead between steps, RDUs use spatial execution to keep compute and communication moving together. That reduces bottlenecks, shortens total time, and improves performance across chips. The result is faster inference, dramatically lower energy usage, and higher utilization at scale. That scaling starts with the RDU. 16 RDUs come together in one Samba rack SN50, purpose-built for agentic inference, and scale up to 10 trillion parameters across 256 chips. Samba rack is ready to deploy in existing data centers, delivering high performance per user and high throughput at cloud scale. Built for the agent era.
Perfect. And now we're actually going to go to a live demo where we'll actually look at how disaggregation is working. So this is being served out of, as Anton said, our VC2 data center, which is Vector Core Compute. And this example is going through a traditional machine learning pipeline, very agentic heavy. But instead of using a normal endpoint, we're actually using a SambaNova dedicated disaggregated inference. So as you can see, we are making multiple requests to the RDU. And of course, because it's an agentic process, we're also using the CPU as well. And what you can see is just how quickly we are running through these. And you can see that we've got the GPU doing the prefill, and then you've got the RDU doing the decode. And it's running through the CPU calls on a dedicated CPU box as well, because we believe that using this different chip architecture for agentic problems will really help you get throughput as you go through this process. So as you can see, we're actually running through the process and we're getting through our modeling, and we're basically going to get out a report at the end of it. Now, we've benchmarked this against B200 only, so basically using GPU only, and we're kind of seeing a 2 to 3x speed up on these workflows. So as you can see, this whole thing has now finished in 45 seconds. And what we'll do is we'll actually look at what it generated, and then we'll actually get into some of the metrics. So as you can see, I had a 10,000 record data set, so it's very pre-fill heavy. And it's generated a very high quality report going through EDA, going through data pre-processing, machine learning selection, and the model comparison and evaluation, and then finally some key performance and insights. So it's a real kind of knowledge task, and when I started as a data scientist, the sort of thing that would take me several days, but now you can see using disaggregated inference, we've really chopped that time down to around 45 seconds. So what we'll do now is we'll actually analyze a little bit the latency, and you can see exactly where the time was spent. So as you can see here, the decode is still the bottleneck. You can see here that we spent 56% time on the RDU, 29% of time on the CPU, and then you can see the GPU doing the pre-fill there as well. So this is real live disaggregated inference, and we're serving it out of vector core compute, and we're working with our partners, and this is live today. And we know that many of the portfolio companies are seeing huge speed ups on their workflows that are very agentic heavy, and we think this is the future. Now, I'm going to carry on and talk a little bit more about premium inference and why it matters. So, on January 3rd, as Anton said, NVIDIA said that the era of general purpose computing is ending. Now, two things are driving this. We think models are moving into the trillion parameter territory, and the way that we use them has fundamentally changed. Let's look at this run here. You can see this is actually a very long horizon coding agent that was running on OpenAI Codex. The active runtime is over a day. You know, this is extra high reasoning. Now, we've moved from simple chatbots to really having agents that don't run for minutes, but they run for days. They plan, they write code, they fix themselves autonomously, and the scale underneath this is enormous. As you can see, almost 13 million tokens. And because of this, we've got a lot of KV cache context reused. So as you can see here, we need to handle a growing KV cache context as well. You can see here that there's almost 26,000 lines of code that were shipped, all in one turn. Now here's what matters. All of this is being served at 250 tokens per user on a frontier model. As we've talked about, enterprises are willing to pay a premium for premium inference. We think that this is only going to become more and more embedded into the market, and it's going to become more of a need than something that's going to be something that you can leave. Now, what we think is that premium inference at high throughput on the highest models is going to be something that becomes the standard and no longer niche. So, let's talk a little bit about 3 ways to disaggregate. So, what I just showed you was disaggregated inference, and as I was saying, we have this live in our data center VC2. Now, we've got 3 different ways of doing this. The first is full decode disaggregation. This is where we're starting. Prefill runs on the GPU, and the decode runs on the RDU. And there's exactly one handoff, the KV cache. This basically plays into the hands of our RDU. We use the advantage, which is memory bandwidth. Now, the second phrase that we've got is called speculative decoding. This is what we're adding. We have a small draft model that speculates several tokens, and then we have a larger target that verifies the batch of candidates there as well. And then in this setup, the RDU can play either role in the deployment stage. And then we're adding it because we think it's going to compound our advantage for even low latency. And as we increase the context of agentic workloads, we think this is going to become really important as well. So finally, we have FFN-only decoding. Now, we're choosing not to pursue this one because it doesn't suit our architecture, and we think the reason why it's being used by the likes of Groq is that it's a shortage, it's a fundamental limitation of the chip, rather than something that, so they're doing it out of a need rather than they want to do it for efficiency purposes. And because of that, we decided to go another route. It's not for us because our chip can handle that, so it's not something that we need to do. So as you can see, there are 3 ways to disaggregate. We are going to pursue the first 2, and FFM we're going to leave because we don't think it's architecturally sound for us to pursue that. And as I was saying in the demo, we are seeing companies already move the workloads to this disaggregated inference, and they're seeing a huge speed up. And we think that's going to increase in the future, and we think that disaggregated inference is here to stay.
Yes, and one last important point that we want to make here, all of what you've seen, all of that, that performance, a real first demonstration of a heterogeneous disaggregated system running in a real production data center at Vector Core Compute's data center in Los Angeles, California. That is an important technology milestone because everybody has been talking about this for a while. Our competitors have been talking about it. NVIDIA talked about it with their acquisition of Groq and the presentation at GTC. We don't believe that this is the right approach. We have demonstrated the approach on the right, which we believe is the correct approach, and that started with SN40. Our SN40 system has been in market now for a few years, deployed at scale in production with customers. The really exciting thing that we're going to talk more about in the next number of months is our SN50 system. SN50 was announced earlier this year. It allows us to really push what is possible on the Pareto frontier, pushing speed to the limit, the largest models, the highest context lengths with really good throughput, things that can't be achieved today on GPUs or can't be achieved today on SRAM-only chips. That in a disaggregated setup, running the latest and greatest GPUs alongside the latest and greatest RDUs, SN50, as well as all of the tool calling offload that needs to go to the latest and greatest CPUs, such as the Xeon 6 Plus from our partners at Intel. That's the heterogeneous disaggregated architecture of the future that's going to enable agentic AI at large scale for use cases like what Kwasi showed, and for the 90+ portfolio companies of Vista, and all enterprise software companies, and then beyond software today, all industries, because all industries are going to be transformed by agentic AI, and this is the architecture to do it.
Perfect. Thank you very much.
Thank you.
感谢 Anton McDonald 先生以及 Kwasi